So welcome everyone. Today I'm going to be working from JMP Pro version 18. JMP Pro is the advanced form of JMP, and it's available if you're interested in it. Everything I'm going to show today is available to you in standard JMP, and it will look exactly like what I'm going to show you in JMP Pro. Everything, the menus, everything will look exactly the same. I am using version 18. So we're going to talk today about reliability for non-repairable systems. And a non-repairable system would be like a light bulb. A light bulb is something that when it fails, screen a little bigger, when the light bulb fails, it's not something that you repair. You throw it away. So those are the class of problems that we're going to be talking about today generally. Here's a simple test for a light bulb. And we're just going to monitor the number of times we turn on and off this light bulb via the switch. And as we go, the things that we might want to know are questions we might ask are, what percentage of the bulbs would fail after 1,100 on-off cycles? 1,100 is arbitrary. Maybe that's a spec that you've got, though. And you want to know how many bulbs would fail after 1,100 on-off cycles. Or you might turn that around and say, how many on-off cycles would cause 50% of our bulbs to fail? Those are the kind of questions that we're going to want to answer. Now, we need data to make our estimates. And some of these test parameters might be that we've got 100 test fixtures in our laboratory, in our test building. So we can test 100 bulbs at a time. Each one of them has a switch or a counter on it to know how many cycles we have applied, how many on-off cycles we've applied to each bulb. Maybe it's a current sensor, whatever that might be. We're not worried about that too much, but we have a way to count how many closures of the switch are applied to each bulb. And if the bulb does not turn on, if it burns out for whatever reason, we know what that count is for each individual bulb. Now we got another limit here. We can only test for a total of 800 hours. The product management has been kind enough to give us lab space for 800 hours for this test to complete. Then we've got to give the lab space back. So that's what we're dealing with. So we start collecting some data. Some of these bulbs fail quickly, maybe after 400 on-off cycles. Some fail later, maybe after 700 on-off cycles. There are a lot of them, of these 100 bulbs, 37 of them, that are still running at the end of our 800-hour time period when we have to end the test. So we're going to plot the results. And the results might look like this. If we bin them, we had a few fail down here after 400 cycles. We had a few more fail at 500 and more at 600, more at 700, more at 800. And then there were these 37 out here that survived to 800 hours that we have to figure out what to do with. Now, we're going to call those censored units. Censoring is the terminology we typically use in life testing to indicate that, hey, this unit was still, it didn't fail. It was still running at the end of our test. Well, what do we do with that? Well, you can kind of imagine if we just threw those away that are in that red band there, we could calculate an average. Maybe we could fit a distribution to these 100 minus 37, 63 bulbs that failed during the test. But that'd be cheating. That's going to make our assessment look too low. These bulbs, the number we get out of that, however you do it, is going to be too low because we had bulbs that went way longer, at least a little longer, maybe way longer than 800 cycles. So what are we going to do? Well, if I click the right button. So these are observed failures. These are censored. Oh, I'm sorry. I'm just making it bigger. I thought I was advancing. So what if we think that the true distribution of failures should be bell-shaped? Well, we could fit a bell-shaped curve to this. It comes up here and then tails off down this way. That maybe has an average here around 800, 850, but this tail has however many the blue bar stack is, that many failures in it. And this we could kind of estimate or guess that these are going to fail on the other side if it's a normal distribution. That's the trick. Is it a normal distribution or not? But that's what we're going to try to do. We're going to try to fit a curve to this to make it to include these censored values that fits the data very well. And then we can extrapolate out and see what's going on out here in the tail that we didn't even measure. This is just, I'm going to skip over this and just go straight into the demo, except I need my data up here. So here's my data. So this is a jump data table. We've got 100 rows in this data table, in one row for each light bulb. And for each bulb, we have recorded how many cycles, on-off cycles, did it take before it failed. So unit 1 failed after 568 cycles. Unit 2 failed after 567. 3 after 726. 4 made it to 800 cycles. And that was, that's where we're ending the test. So I guess we're doing one of these cycles per hour, kind of a strange test. So for that particular bulb, we're going to say that that was censored. We have a 1 here for censoring, saying that at 800 cycles, that bulb was still operating correctly. And the same for bulb 5. And then bulb 6, it failed after 734 cycles. So this is the data format that we're going to use to estimate the life of these bulbs. So we're going to go to Analyze, Reliability and Survival, and then right up here at the top is Life Distribution. And we're going to let JMP do all of that estimation for us. Let's see, we've got cycles to failure. That's our time to event. It says time here, but it doesn't have to be time. In this case, it's cycles. It's on-off cycles. It's whatever that unit is that you're stressing your part. You're turning it on and off. You're vibrating it, or maybe it is time. Maybe it is just a number of hours. But whatever you're recording that is the failure, that is stressing the product of failure, is what we put here. So that's cycles. The sensor column goes here. So this is telling JMP, oh, okay, we've got some parts that failed, some parts that did not fail. And over here, we get the opportunity to say, what's our code for what has failed and what hasn't failed? So if it's censored, in our case, like part 4 here, we put a 1 in there indicating censoring. And so we'll just leave that as is. You can flip that around if you need to. Okay. So we'll say okay. And we get the life distribution platform and report. Now, the first thing that we get, JMP always just gives us the data set, the raw data. And as we can see here, this plot is just a linear scale versus a linear scale. And it's got some curvature to it. You can see that. These are each of our measured failed devices. One bulb down here at row 16 failed after almost, 400 cycles or so. So 16 years, 422 cycles, and so forth. Every one of these is a bulb. These up here, this little blob of points that are all laying on top of each other, are all of the censored bulbs. So they made it out here to 800 cycles, but and they had not failed yet. One question that pops up a lot is, do you have to run all of those bulbs or try to run all of them out to 800 cycles? And the answer is no. maybe there's something that broke in your fixture for one of the bulbs after 550 hours, one of the wires broke or melted or something. That bulb didn't fail, but it only made it to 550 cycles. So that would be censored. So we'd have whatever that bulb number is, say right here, we'd say 550 and a 1 out here to say, hey, it was censored at 550 cycles. So you don't have to have everything fail out here at 800 cycles or be censored at 800 cycles. Okay, so this is just our basic data. JMP does do what's called a non-parametric estimate of where the failure line, if you will, might occur for these data. So here at let's say 700 hours, I think somewhere the measured value appears to be somewhere around 32, 33% of my product will fail, but there's a confidence bound around that says it's really 25% up to 42%, just eyeballing it a little bit. But we can do better than that. We've got all these other distributions, parametric distributions that we can fit. For instance, here's the normal distribution that we were talking about earlier. So if I turn the normal distribution on, I can see this is how well the normal distribution fits that data. And it looks pretty good. It fits it pretty well. And in fact, if we did a kind of a normal probability plot by clicking on the scale button, what JMP will do is adjust the scales so that if it's a normal distribution, it will appear to be a straight line. The data will follow along a straight line. Now we can try others. We can say, well, what about a Weibull distribution? Let's see what a Weibull distribution looks like, and I'll turn off the normal. So it looks, other than these couple of points down here, that looks like a pretty good fit too. What about the logistic fit down here? Well, even that one doesn't look too bad other than these points down at the bottom. So how do we decide which one is the best fit? Well, I'm going to turn that off for the logistic and set this back to non-parametric. And I'm going to come up here to the top and say, I want to fit all distributions. So JMP's going to go through and fit all of these. And there's some down here further down in the list that have got a lot of different characteristics that have become, that people have decided can be used, are typical for some of the data that they have analyzed. So we're going to go in here and say fit all distributions. JMP will then fit all of those distributions and pick the one, in this case it's called the log normal distribution, that it thinks is best. And it'll adjust the scale so that we can see this is the fit that it got. Well, how did it do that? That's summarized down here in the model comparisons. And in particular, we're looking for this thing called the AIC value. So here the AIC value is, we're looking for lower is better. And so if I looked at, say down here, the exponential has a 915 compared to the log normal of 799. Let's see what an exponential looks like. Oop, where did it go? Oh, there it is. So there's the exponential distribution. Clearly, it's not a very good fit. So that's what these do. The AIC value is, if you're within a couple of points, maybe up to 3 or 4 points, all of these models are essentially modeling the same, just as well as each other. It's kind of within the statistical significance that these models aren't different. So if you knew, based on the physics of your process or your product, that Weibull is the one that really should be applying here, you can look here and say, yeah, I could pick any of those and they'd be fine. So I'll change up here to Weibull. Okay, so now we've got a Weibull distribution. Now, what do we do with that? Remember, there were a couple of questions that we wanted to ask. One was at 11 1,100, if I remember right, at 1,100 cycles, what percent of our product would fail? So I'm going to use my distribution profiler, just like any other graph in JMP. We can drag things around and look at it. And I can, in fact, type in here 1,100. And it looks like, wow, just about all of our product is going to fail. 99.5% of our product will fail by 1,100 cycles. How about it if somebody asked me, well, what about 900? Well, by 900 cycles, we think that 81% will fail. Now, there's a confidence bound on that. Between 69 and 90%, we think will fail. Our best guess is 81%. So that 69% would be a conservative estimate for us. So we can pull that right off the chart here. If I scroll on down a little bit, here's that same distribution profiler. This is exactly the same as we saw above. But we've also got here a Quantile profiler. The Quantile profiler flips the axes. So our cycles to failure is now on the y-axis and our probability is on the x-axis. So we can grab and drag around here and say, well, when do I think 40% of my product will fail? Well, it's at 725 cycles. All right, so that's a very brief overview of what happens in the life distribution platform.